we're going to start off where we left in class. So here's the next slide. We left at talking about cooling curves. So next part of our notes, forces. What actual forces are being dealt with in each of these situations? So the first one, dissociating F2. Dissociating is a fancy way of saying breaking bonds or pulling the F2 apart. Not pulling an F2 apart from another F2, but literally pulling apart F2 into two different Fs. So what kind of force would that be? At any time during this, if you want to be thinking about it, pause it before I give you the answers. I'm not going to be giving you a lot of time to think about it. So after I ask the question, if you'd like to pause it to think about it, you can do that. So the answer for this would be intramolecular forces, not intermolecular forces, which are IMFs. Intra are the actual bonds or forces that are within the molecule, not between molecules. So that's a big differentiation that you have to try to figure out here. We are breaking apart the force that's within the molecule, not between the molecule. Next one, boiling H2O. Which one would that be? Boiling is about a phase change. In a phase change, I'm going from a liquid to a gas. So I'm not actually changing the compound. It's still H2O. It's H2O as a liquid. It's H2O as a gas. So I'm not breaking apart the bonds between the O and the H within the molecule. I'm breaking the attractive forces and bonds between the molecules. So that is an IMF. So then you have to think about what kinds of IMFs are present in there. And I see an O to an H. So that would be considered hydrogen bonding. Boiling liquid Br2. So again, phase change. So I think IMF. And this time Br2 is nonpolar. And nonpolar would be London dispersion forces. So those are some of the forces in some of these situations. All right, here we go. Interactions. There's a lot of them here. What is the major IMF? Here is a word bank. You have London, dipole-dipole, H bonding, and ion dipole. All right, so what I want to know is the following four. And again, I'd pause it and let you figure this out yourself. But I'm going to continue on. So if H2O and CO2 interact, what is the answer to that one? The answer is hydrogen bonding. And the reason why is that you have OH here, and then you have oxygen here. So the oxygen would actually be attracted to the H here. All right? You could maybe have debated that if it was hydrogen bonding to dipole, but the fact that hydrogen bonding is still considered hydrogen to oxygen or fluorine and nitrogen. So this actually, the bond would be between the H and the O in that case. So that would still actually fall under hydrogen bonding. I know that can be a little confusing. CH4 and Cl2. The answer is London. The reason why? Nonpolar, nonpolar, all that's present are London forces. NaCl and pH3. This is a salt. Salts break up into ions. This is pH3. You have to remember that this has a lone pair on it. So this is polar. So the answer is ion dipole. The ion is the NaCl, and the dipole is the pH3. The pH3 is going to surround the ions. So then finally, last one is dipole-dipole. The reason why, this is actually a seesaw. It's a polar substance. This one is a tetrahedral. It is also polar. Because they are both polar, it creates a dipole-dipole. Greater surface tension. You got N2 or you got Br2. Like all of the things, we need to break down what type of IMF is present. The answer is Br2 is the stronger of the two LD forces because it has a larger electron cloud. They are both LDs. So the larger the cloud, the stronger the IMF. Lower melting point. C3H8 or CH3OH. What are we looking for at lower melting point? We want weaker IMFs. So which one has a weaker IMF? The answer is, this is very symmetrical and even, so this is nonpolar. This has hydrogen bonding, So C3H8 has the weakest IMF, LD versus H bonding. Lower the melting point means the less energy needed to overcome the forces holding the molecules together. All right, of these four options, SO2, CCl4, CH2Cl2, or H2S, which one is primarily London forces? So we're going to slide over to the board for a second. And what is really important about this one is that you need to understand what the shapes look like. All right, so some of these you may get a little confused on. For example, some of these are a little more straightforward than others. For example, CL4, this is tetrahedral. This is also tetrahedral. This is bent. And SO2, a lot of people would make a mistake on this. If you add it all up, it is also bent. So what does that mean then? This is dipole-dipole. This looks very much non-polar. So this would be LDs. This is polar. So that would be dipole. And lastly, this is not H bonding. This is also just polar. This is also dipole. So the answer would be CCl4 is primarily London forces. Higher melting point. HF, H2O, HI, or HF. Again, what you need to do is figure out the IMFs that are present. Please do that. These are the answers, and one is incorrect. This right here is H bonding. Why do I have two of the same? All right. So higher the melting point, what you need to realize then is that you need a stronger IMF. So it's between these two. Due to the fact, even though they both have hydrogen bonding, the fact that water has two hydrogen bonds versus HF only having one hydrogen bond would mean that the answer would be the H2O. H2O has a stronger IMF with H bonding, while the others are all dipole-dipole. Excuse me, that's not quite correct. H2O would require the most energy to complete to overcome the IMFs to turn it from a liquid to a gas. Most viscous. Viscosity is the resistance to flow. Here again you have C3H8, CH4, C2H6, and C6H6. They are all London. So then what is the answer again? With all of these different characteristics of liquids, except for vapor pressure and volatility, the higher the property usually refers to the higher the IMF. So I want the strongest IMF here. In this case, they're all LDs, but we know something about that, and that is the larger the molecule is, then the larger the electron cloud would be. And C6H6 is the largest of all those. So C6H6 would have the highest viscosity. All right, finally, we're going to finish by making a phase diagram. So the pressure here is in ATM, temperature is in Celsius. I want to make different points here. So you got to understand what you're trying to draw. And you got to understand that sometimes it's not going to be to scale. So what I want to do is just kind of look at different points. The highest value here is 72.8. Okay, I'm just kind of looking at different ones here. This is 5.1. This is 1. It's not to scale. It was just what was given. So I have 72, 5.1, and 1. Temperatures, again, think about what you're given. I have 31 degrees. I have negative 56.6. And I have negative 78.0. And don't worry about that if it's the scale or not. You just need to make sure that it's in the proper order. So then what you can do is you make these points. So it says the Sublimes at negative 78. And maybe I'm not doing this great. We'll find out. 5.1 and negative 56 is the triple point. And the critical point is 72.8 and 31. Okay. What that means is a couple things. Is that if it sublimes on this bottom point right here, that is the barrier of the solid, the liquid. So I'm not quite sure exactly how this is going to go, but it probably looks something like this. Okay? And then this value goes all the way up here and it stops. And unfortunately, we are actually missing a point. So we will have to add that data. So I apologize, you have to add something here. So let's just say it's this. The freezing point is at, I'm ad-libbing this, 10 ATMs and negative 36 degrees. So if I do that, let's put it right about here, negative 36, all right? And I'm going to make a value of 10 ATMs, which will go right about here. It's not to scale necessarily. So I make the point and it goes like that. Okay, so then what does that mean? From here, it goes up like this. So then what do I have? I have my solid and my liquid, and I have my gas. And what that probably means then that this would probably be the boiling point. And this would be the freezing point or the melting point, either one you want to call it, okay? So then I could ask some different questions. I could ask, is the solid or is the liquid more dense? Well, because of this shaded area, it's all above the liquid, and the fact that this line right here is a positive slope, I would say that the solid is more dense than the liquid. I could ask, when I'm at 1 ATM and negative 56 degrees, if I continue to lose energy, what process is occurring? Well, in this case, it's deposition. If for some reason I said that that was at 10 ATM and 31 degrees, what process would that be? So I'm up here now, and I start to lose temperature. Well, what's that? Going that direction? That's called condensation. So we could ask about all sorts of different directions and what process occurs in that phase diagram.